Here we've been asked to sketch the graph of sine inverse of sine of x. And we need to be careful, because if we're not careful, we might naively think, well, sine of x gives me a number between -1 and 1, and inverse sine takes that back to the angle I started with, and we might just write x. And think the graph of this is always just y equals x, but if I graph that, what I realize is, I get the whole line, right, y equals x, but that I have y values above 1 and below -1 on there, and those can't possibly be part of this graph, because inverse sine can only tell me numbers between minus pi halves and positive pi halves. So that approach won't work, because I need to remember the range of inverse sine. So maybe to start, we just write down some things we know to be true about this function, its domain and its range. And in the end, inverse sine is going to take a bunch of values and give me angles between minus pi halves and pi halves. Only those. The domain, if I think about how to find the domain of a composition function, I'd first write down the domain of the inside function. Well, sine has a domain of all real numbers. I can plug in any angle measured in radians I want to the sine function. And that will give me a number between -1 and 1. Well, all of those values are in the domain of inverse sine. And so there's nothing to throw out at all. And I could plug in any real number I wanted to this function. And so when I'm thinking about graphing it, the domain, all real numbers, but the range is limited. So here I need to think about all of the angles going on forever. And I'm just going to be counting in multiples of pi halves here because, well, I'm used to doing that when I'm thinking about these kinds of trigonometric graphs, and I think it'll make sense in a moment too. But on the y-axis, I'm going to go up to pi halves, and I'm going to go down to minus pi halves, and I know the entirety of my graph will lie in that strip, because the only y values I can get out are between minus pi halves and positive pi halves. So let's do the easy part first. And let's just imagine doing the little bit of the graph that lives between minus pi halves and positive pi halves. Because that is the part where we would have been okay if we did this naively, right? Because if I plug in minus pi halves, I get the sine of minus pi halves, which is -1. The inverse sine of -1 is sine of, it's just minus pi halves. In there, where everything is nice and well behaved, that's where we would get y equals x. That's where those two functions do undo each other. If I think about the restricted domain I used for sine when I found the inverse function. Now outside of this, we have to think a little bit more cleverly. So now let's imagine the angles between positive pi halves and positive pi. If I think about this function composition in the first quadrant, it was really boring. Sine takes an angle to a y-coordinate, inverse sine takes that y-coordinate back to the angle. And in the first quadrant, there are no problems. It's just I get the angle back I started with. So this just equals x. But when I pop over to the second quadrant, inverse sine can no longer tell me this larger angle theta. But it can give me this angle over here, its reference angle, right? Because sine has the same value there. So sine of this angle theta becomes a y value. Inverse sine of that y value becomes this angle in the first quadrant, where sine is also positive. Well, if I think about what's going on there, the moment I go past pi halves, I get an angle like right there at the same value, right? The reference value is the same. And then I think about those y-coordinates, they would go back down until I got to pi. And so I get another line segment, it just has the opposite slope, and that didn't look like a line segment to me. As I get into quadrant number 3, I have to think about reference angles again, but now inverse sine's giving me an angle over here in quadrant number 4, a negative angle. And I think after doing just that much, we see what's going to keep happening. We're going to keep getting these line segments that are kind of flipped over each other. And what we see is a sawtooth function. Now let's make sure I'm not lying to you and see this actually graphed to scale. So let's get out our TI-83s, TI-84s, whatever graphing calculator you have. We'll make sure we're in the radian mode. And we can type this function in, sine inverse of sine of x. And I'll close both parentheses to be a good little math student. All right, so what I want to do now is set up the window. So I'm going to go into the window, and I want to graph from minus 2 pi to positive 2 pi on the x-axis. And to make it look like what I've sketched here, I'll put a tick mark at every pi halves. On the y-axis, I don't need to graph nearly as much. I'm going to go from minus 2 to 2, even though I know there are no y values between 1 and 2. I think I'll like the way that looks better, no real reason there. And again, I'll put tick marks at every pi half, so it'll look like the way I split this up, and I think I'm ready to graph this. And there we see our sawtooth function. Sawtooth functions come up every once in a while in the study of electrical circuits, but that's it for this video.